Good morning. All right. Starting our study of the geometry of space. This week we look at objects in space. Lines, planes, and surfaces. Line L is parallel to a vector V, given as ABC, passing through the point x0, y0, z0, can be described by the set of parametric equations x equals x0 plus ta, y equals y0 plus tb, z equals z0 plus tc. Right, t is the parameter, and for a line, t will range over all real numbers. As long as all of your constants, a, b, and c, are non-zero, we can also write the line using its symmetric equations. X minus x naught over a equals y minus y naught over b equals z minus z naught over c. Right, we just solve for t. We have a line L, passes through point P with direction vector V. If M is any point that is not on the line, the distance from M to L. Magnitude of the directed line segment, that should be PM, cross V over the magnitude of V. This will give us the shortest distance. Now think back to when you studied lines on the plane. You have two lines on the plane. What were the possibilities for the lines? How could they be related?
Parallel.
Could be parallel. There's two possibilities for parallel.
Same direction and not together.
We're talking about lines, not directed line segments. It's either the same line or it's not. Right, parallel lines, it's either going to be the same line, right? Every line's parallel to itself. Or it's a different line altogether. And then what else? What other relationship is there? That is a special case of the relationship. They intersect. But they can intersect at any angle. In space, we get a fourth possibility. They're what's called skew lines. They're neither parallel nor intersecting. Right, so your lines either equal, parallel, intersect, or none of the above. Plane. Given a point P, a vector n, set of all points Q satisfying the equation n dot the line segment PQ equals 0 forms a plane. That is our definition for a plane. This equation is known as the vector equation of the plane. Scalar equation of the plane. So plane contains point x0, y0, z0. Normal vector is ABC. Your scalar equation A times x minus x0 plus B times y minus y0 plus C times z minus z0 equals 0. Right? It's called normal vector because it's going to be perpendicular to the plane. Then we have the general form of a plane. AX plus BY plus CZ plus D is equal to 0. where D is negative AX naught minus BY naught minus CZ naught. And there is one more equation. I think it's standard form, where you just move the D over to the other side. AX plus BY plus CZ would equal negative D. For the most part, I'll be sticking with the general form for a plane. Distance from a point to a plane. Again, by definition, we take the shortest distance from the point to the plane. We have a plane normal vector n passes through a point Q, so it contains the point Q. Distance from a point P not in the plane to the plane is the magnitude of the projection of the line segment QP onto N. Which, if you remember that formula, you can easily work out. Absolute value of the direct line segment QP dotted with N over the magnitude of N. Or we can rework this, do some algebra to get that equation. Bless you. Set of Pound's equations for the line passing through the point 1, 2, 3, parallel to any line that has direction vector of 2, -1, -4. That's the first thing they want us to do. Then they're going to want us to determine which of those 3 points are on the line. And then we will use a graphing utility to plot the line. So we have our point, right? So we have our x naught, y naught, z naught. Do we have a direction vector? What is it? And if our line's going to be parallel to any line with that direction vector, it's got to have the exact same direction vector, right? Do you have a question?
No.
Right, so we have our direction vector too, which makes this really easy. They gave us both. All right, set of parametric equations. X equals x naught plus a times t. Y equals y naught plus b times t. Z equals z naught plus c times t. So I'll represent it. Line is L. With that set of parametric equations. And math trivia time. That is a mathematical symbol. Called L. So if you're typing in LaTeX, you want that symbol. That's its command. /ELL. If we want to determine whether the points are on the line, two ways we can go about it. First way, using that set of parametric equations, what do you think we'd have to do? Assume you don't have access to graphing. So I want to do it algebraically.
Do you plug in the numbers from these to like T?
Not in for t. In for your coordinates. X, Y, and Z. And then solve for t. If there is a t, you're done. If there's no t, then there's no solution, which means it's not on the line. That is a bit of a pain, though. There is a second method that can be used on certain lines. We also have symmetric equations. As long as none of the components of your direction vector are 0. Which in this case, there are none. Right, none of them are 0. So we can use the symmetric equations. which is what we're going to do here. And so we're going to represent L now with the symmetric equations. What are the symmetric equations?
X minus divided by and negative
So give me the x1 for this line. X minus what over what?
X naught over A.
Right. What's x naught and what's a? What does that equal?
how do you calculate that?
Solve for t. That's the easiest way to do it. X minus 1 over 2 equals, what's the next term? Solve the y equation. What is it? I'm not going to write that way just yet. That is how I'm going to write it in the end. Y minus 2 over negative 1, right? Just solve the y equation for t. Which equals what? What's the third term? Over what? There's our line. Now what we can do is just take each point and make sure that that equation is satisfied. If the equation is satisfied, it's on the line. If it's not satisfied, it's not on the line. A was 3, 1, negative 1. Three minus 1 over 2. 2 minus 1. 3 minus negative 1 over 4. A is on the line. Because it satisfies the symmetric equations. Remember, that is how we're representing the line. So if any point on the line has to satisfy that. And so when you plug in your point A, you get 1 equals 1 equals 1. Satisfied. Now point B Yes, let's throw fractions in there, because why not? Half minus 1 over 2 has to equal 2 minus 9/4, which has to equal 3 minus 4 over 4. What's a half minus 1 divided by 2? 2 minus 9/4. -1/4. And 0.25. What is 3 minus 4 divided by 4? Yeah. -1/4 equals -1/4 equals -1/4. B is on the line. C is the 0.201. 2 minus 1 over 2 has to equal 2 minus 0 has to equal 3 minus 1 over 4. 2 minus 1 over 2. 2 minus 0. 3 minus 1 over 4. That is a contradiction. Half equals 2 equals a half. Which points are on the line? A and B are on the line, C is not. Let's see if that is big enough. Oh, yeah. So doing that reminded me, this is kind of scary, actually. This popped up on my feed yesterday. The apocalypse is beginning. This is how the zombie apocalypse starts. Actually, that's not how it starts. How it starts is scientists want to study that fungus because it has medicinal properties, apparently, for humans.
Have you seen the robots spider corpses?
They're going to be introduced to my best friend called Flamethrower. Spiders are fine as long as they're not in my house. I actually had a pet spider who was hanging outside my window. I said, he's not in the house, so he's cool. As soon as you come in the house, you're dead. Bees are a whole nother story. No, you can even be outside the house, there's still a flamethrower. So, yeah, lovely. I'm joining Team Zombie. This is what I want though. So I think this is our first look at Mathematica for the semester, isn't it? Want to plot the line. Given a set of parametric equations, we want parametric plot 3D, and that's not good. That means Mathematica is not quite awake yet. Unless it, oh wait, it did update. Did they change it? They changed things. Bet they did. With any kind of Mathematica function, what you're applying the function to has to be in brackets. And so it'd be parametric plot 3D. Notice the capitalization commands. Brackets. Put in braces. Your x equation. Your y equation. Oh God, they did change it. Perfect. And your z equation. Now they highlight them instead of actually having the text be the color. Oh. Another set of braces. What is your parameter? Lower bound for the parameter and upper bound for the parameter. Let's just start with minus 10 to 10, see how that works. That is all you need. To execute, shift, enter. Yeah, it's not awake yet. It's going to take a while to run. Oh dear. Why are you doing this to me? Should not take this long. Notice over here, this indicates the nestings. And you see how it's bold, that means it's still running. And it shouldn't be taking this long. I'll try to restart it. No, oh, Pete's sake. Oh, yes. Okay. Excellent. It's awake. So they didn't change it. So notice text right now is blue. You can't see it, but it comes up with a listing of possible commands you could mean. Now notice if I don't capitalize the P in plot, it stays blue. That means that is not a command. It's now reading that as a string. Text change black. That is a command. However, that is for 2D. That is now a recognized command. Right, and you should see the T is blue. Again, it's a string. It's reading as a string. It should turn green. It didn't. There it is. Yep. Now it's being stored as the actual variable for the plot. And this is, again, technically all you need. So Shift Enter. And there's your plot. There's a few things I don't like about this plot. First, the default colors in Mathematica are really ugly. So I never use the default colors. Unless I absolutely have to. Second, when you think of a plot, do you think of it as boxed? Or do you think of the axes intersecting at an origin that's in the center? So I'm going to change those. First thing I'm doing is changing the hideous color. What color do we want? Let's go with one of the brown colors, brown. Why not? So it has some built-in colors already. But my favorite feature if you know the RGB code, you can also use any color using the RGB color command. It also has CMYK. You want to use the CMYK code instead. So do that. Boxed is on by default, so I'm going to turn it off. If I do this, this is now what we have. So there's one more thing I have to specify. Set the origin to actually be the origin 0, 0, 0. And there you go. However, unless you are really familiar with Mathematica, which axis is which?
The axis going in.
You would think. That's not how Mathematica does it. Z is up.
The Y.
Mm-hmm. And also notice that they have the negative coming out at you, which is why this is a right-handed system, with that being Y, because the positive Y is actually going into the screen. But once you start moving it, because you can move it, it's very easy to lose track. So you can turn axes label.
Can you change it to remote?
Yeah, you have to rotate it. Or, I'm trying to think. I'm also going to change the label style to bold, just so you can see the labels a bit better. So there are two ways you can, if you notice, I scroll my arrow over, see how it turns to the, if you right click, you can then start to rotate it. Right, all kinds of ways. You can also use what's called the viewpoint command. And then you can set different points. But again, there's also some built-in ones. Front, back, above, below, left, right. Normally you would think you'd want front if you want to look down the x-axis. Unfortunately, I don't think that's what they do. No, Mathematica puts y as the depth, not x. That would be your front view, looking down the x-axis. And then I can kind of rotate it just to, I don't know, be a little bit better. And maybe tilt it just a little bit to make the x-axis a little bit more visible. I don't know. That kind of looks good. Right, there's no real rule on how to post it. Generally speaking, what you want to do is you want to pick a viewing angle that gives you the best idea of what's going on. For a line, it doesn't really matter. It's just a line. When we start dealing with multiple integrations and we want to start looking at surfaces, the viewing angle is going to be really important. So we have to play around with it. Okay, so now what I'm going to do is, again, you're not going to be able to see it. But over here, see this nesting here? If I click it, left click it, again, you can't see it. There's a window that comes up. One of them's convert to. I'm going to convert it to bitmap, so it turns into a photo to make it easier to copy and paste. Copy image, and then paste it as a picture. And there it is in our slide. And so you have to do any kind of graphics for a project using Mathematica, that's how you do it. I'd recommend you convert it to a bitmap, then copy and paste it into your actual document. That generally just works better. Don't worry, we'll be using Mathematica a lot more in the future. One of you will probably become an expert at it by the end of the semester because of linear algebra. And we're going to be using it a lot in linear algebra. Unless you want to do all that work by hand. Yeah. I'd recommend Mathematica. I don't know if does Desmos do matrices? Yeah. Yeah, well, Mathematica does, and that's what we're going to be using it for. So we want equation of the plane that passes through the point P naught equals 1, 2, 3. Oh, joy, if this is the time they go out there every day, then your exam's going to be fun. And parallel to the plane 3x minus 2y plus 4z minus 5 equals 0. And then we want to plot the plane. It would be nice if you had that much energy this early in the morning. Not to be like that, I'd need like 8 cups of coffee. And by then it's usually noon.
But if you're not stressed out, do less reading.
Yeah, I got 2 of them. One of them has unlimited energy, I swear to God. He'll not nap all day and just, that'll be it. He'll do that all freaking day. Freaking. Just hook him up to a treadmill and somehow convert that into electricity. Get a human-sized hamster wheel. Just let him run on it. He'd probably break it within a day, though.
Save on your energy bill.
Yeah, except he'd break it within a day. He'd overuse it. So let's say here's our plane of interest, right? So what do we know? We know already, it told us, it contains some point. I'm going to call this plane 1, capital Pi. This is what we typically use to represent a plane. The problem told us it's parallel to another plane. Let's call that plane 2. And we know that they're parallel. All they gave us here was the equation of the plane that's parallel to. But can't we determine its normal vector from the plane or from the equation? We need a normal vector for P1, pi 1, right? Call that normal vector 2.
So a normal vector that is unit.
It doesn't necessarily have to be unit. It just has to be normal. Well, if pi 1 and pi 2 are parallel, how would their normal vectors relate? Which means what?
Same magnitude.
They don't have to be the same magnitude. And they technically don't have to have the same direction. They're parallel, right? So that's going to be the same direction or a complete opposite. Right? Magnitude doesn't matter. All that matters is the direction. So N1 and N2 also have to be parallel. This means N1, isn't it just going to be some scalar k times N2? That's the definition of vectors being parallel. Why not let k be 1? Then you have the same normal vector. Which means we have the information we need here. We already have our point. What is the normal vector? You're overthinking it.
Just 3 minutes.
The normal vectors is 3, -2, 4. Which makes our plane 3x minus 2y plus 4z plus negative a times x naught minus b times y naught minus c times z naught, and then equals 0. -3 plus 4 is 1 minus 12 and there's the plane.
Wait, why does it have to be put this way?
That's the general form of a plane. AX plus BY plus CZ plus D equals 0. Remember that?
Why is the X kind of not as one? Why is that the that's
Where am I? There I am. So if you actually do the algebra out on the scalar equation, which you can get from the vector equation, that's what you find for D. Negative A times X naught minus B times Y naught minus C times Z naught. Right, because you're going to be distributing that A, the B, and the C through. And those are all constants, so you group them together. See that?
why is the normal vector like the same slope as the plane? Shouldn't it be?
Because the planes are parallel.
But shouldn't it be perpendicular?
It's perpendicular to the plane. But if you have two planes that are parallel, their normal vectors would also have to be parallel. Right? Plane 1, plane 2. Normal vectors are always parallel, right? That's why.
The point is passed through the plane.
Right, it's a different point passing through the plane.
But so is the end vector the normal vector?
For both of them, yep.
But if the plane is 3x minus 2y plus 4z, and the vector is 3, 2, 4, when they become direction.
We want the two normal vectors to go in the same direction. And if they weren't going the same direction, then your planes would not be parallel.
And I'm just confused on why, like, comparing the normal vector to the given plane, they look like the same thing, ignoring the other plane.
They are. Remember, how you draw your coordinate system doesn't matter when dealing with vectors. So you can just move your second plane to overlap the first plane. The normal vectors are exactly identical. So that's why you can just use the exact same vector. But notice the constant, the D, is different. That's what gives you your different set of points. And that's why the two planes are not the same. And by the way, I could have also used n where you double each component. So parallel, right? Notice that all of your numbers then would then be doubled. So you'd still get the exact same equation when you factor.
Because they're just being scalar.
We want to plot the plane. Can use plot 3D. You'd have to write it z equals a function of x and y, which you can do for a plane. It's not that difficult. However, it has problems. I never use plot 3D. So I'm going to use contour plot 3D. This allows me to write it as a relation. All right, so we said the plane was what? 3x minus 2y plus 4z minus 11, and then equals 0, right? Because it's a test, single equals says you're setting that equal to 0. A double equals means you're testing that it equals 0. So this would be the set of all points x, y, z, where that equation equals 0. So you have to do a double equals for this. Now we need bounds for the 3 variables, x, y, z. What do I want to do? Want to do the box minus 5 to 5? And again, that is technically all you would need. But it gives you that hideous thing. That is not appealing. I am also going to shut off the mesh. That's what gives you those grid line-like things. That looks better. I think if I do that, I can then change, not plot, sorry, contour style. Yeah. So if I turn the color function off, I can then change the color of the plane. Versus if you leave the color function on, I don't think it works this nicely. No, maybe it does. Let's do pink. They call that pink. That's not really, yeah, that's not pink. So Mathematica is a little bit colorblind, but it's okay. All right, let's to look down the x-axis. And I can just kind of rotate it just a little bit to get a better, like that, sort of. I just get a better viewing of all the axes. I don't know if that works. Now it looks kind of red. I think this is where I need to turn the color function off. So I'm going to return that to none. No, it still kind of looks red. No, whatever. Now remember, you're not actually cutting off at the the top right, that plane extends out indefinitely in all directions. The reason you have that little cutoff is because we're restricting the bounds for the X, Y, and Z. So you're never going to be able to actually remove that cutoff truly. That's it. There's the plot as well. So what else do I have to do this week? I think this week is also cylindrical and spherical coordinates. If I remember correctly. Right, so we have to finish this up. We're going to do surfaces in space and then look at cylindrical and spherical coordinates. And your first quiz is this Friday. We'll go live on February 7th. And it covers everything we've done so far, up through and including Friday. Goodbye.
What do you mean it goes live?
That's when it becomes available. So right now you can't go on there and take it. It becomes active on February 7th.
It shows on 11.
Yeah, sure.
That's when it should be due.
No, yeah, it is the 11th.
Yeah, that's not when it's available. It's due the 11th. So to be able to access it from the 7th to the 11th, because I have it set to no longer be active after the due date. So you have a homework coming due the 6th and the 7th. The next homework 4, will go up Thursday. And that's the stuff, lines and planes. Maybe surfaces as well. I have to double check the WebAssign actually.
I'm actually having the same issue with the guys. I'm just checking.
So I'll see you on Thursday.